In 1978, two NASA scientists named Donald Kessler and Burton Courpellet published a paper in the Journal of Geophysical Research that described a scenario they called collision cascading in Earth orbit. The scenario they described was this. As the population of objects in low Earth orbit, satellites, spent rocket stages, fragments from previous collisions and explosions, grew denser, the probability of collision between objects would increase. A collision between two objects in orbit does not produce the kind of localized damage that a collision at terrestrial speeds produces. At orbital velocities, 7 to 8 kilometers per second in low Earth orbit, a collision between even small objects releases kinetic energy equivalent to an explosion. A collision between two larger objects generates not two damaged objects, but thousands to hundreds of thousands of fragments, each moving at orbital velocity. Those fragments become new projectiles. Each new fragment is capable of colliding with another object, generating more fragments. Under certain conditions of orbital density, this process becomes self-sustaining. The fragments from each collision generate enough additional projectiles to produce further collisions, regardless of any new objects being added to the environment. The cascade, once initiated, continues independently of human activity. This is Kessler syndrome. It is named after the scientist who first quantified its dynamics. And the question of whether the current population of objects in low Earth orbit is already approaching the density threshold above which cascading becomes probable, and what the consequences would be if it began, are among the most important questions in the space domain. The current population of trackable objects in Earth orbit is approximately 27,000, as cataloged by the United States Space Surveillance Network. These objects range from active satellites to defunct spacecraft to spent rocket upper stages to fragments from past collisions and anti-satellite weapon tests. The trackable population represents only a fraction of the debris environment. Objects below approximately 10 centimeters in diameter are generally not individually trackable with current radar capabilities. Estimates of the total debris population include approximately 500,000 objects between 1 and 10 centimeters and tens of millions of objects smaller than 1 centimeter. Below approximately 1 centimeter, objects cannot be individually tracked, cannot be avoided by maneuvering satellites, and cannot be destroyed without generating more fragments. The kinetic energy of even small objects at orbital velocity is significant. An object 1 centimeter in diameter moving at 8 kilometers per second carries kinetic energy equivalent to a hand grenade. An object 10 centimeters in diameter carries energy equivalent to a small explosive charge. The International Space Station, which orbits at an altitude of approximately 400 kilometers, is regularly maneuvered to avoid tracked debris and is equipped with protective shielding designed to handle impactors up to approximately 1 centimeter in diameter. Impactors above this size cannot be stopped by shielding and must be avoided by maneuver. Several events in the past 2 decades have substantially worsened the debris environment in ways that make Kessler syndrome more rather than less likely. In 2007, China tested an anti-satellite weapon by destroying one of its own weather satellites, the Fingyun 1C, at an altitude of approximately 860 kilometers. The impact generated approximately 3,000 trackable fragments and an estimated 150,000 fragments above 1 centimeter. The altitude at which the test was conducted is particularly problematic because orbital decay is very slow at 860 kilometers. The fragment from this test will remain in orbit for decades to centuries. In 2009, the operational American satellite Iridium-33 collided with the defunct Russian satellite Cosmos 2251, generating approximately 2,000 trackable fragments. This was the first major accidental collision between two satellites and demonstrated that the debris environment was already capable of generating significant cascading debris through unintended events. India conducted an anti-satellite test at a lower altitude in 2019, generating fewer long-lived fragments, but contributing to the tracked debris population and generating international concern about the cumulative effect of similar tests. The growth of megaconstellations, very large numbers of small satellites deployed in low Earth orbit by commercial operators, including SpaceX's Starlink, Amazon's Project Kuiper, and others, has added thousands of additional objects to the low Earth orbit environment in recent years, with plans for tens of thousands more. Each object, if it fails and cannot deorbit under its own power, becomes a permanent debris contributor. The operators of these constellations have implemented deorbit plans, but the reliability of those plans over the lifetime of thousands of individual satellites, some of which will inevitably fail before they can be maneuvered to lower orbits, is an open question. The consequences of a Kessler syndrome cascade in low Earth orbit, the altitude band between approximately 200 and 2,000 kilometers, would be severe and long-lasting. Low Earth orbit is where the most practically important satellites operate. Imaging satellites, weather satellites, some communication satellites, and the International Space Station all operate in this altitude regime. GPS satellites operate at medium Earth orbit, approximately 20,000 kilometers, and geostationary communications and weather satellites operate at 36,000 kilometers. A cascade in low Earth orbit would not directly affect these higher altitude assets, but access to low Earth orbit would become extremely dangerous or impossible. Launching new satellites through a debris field dense enough to sustain cascading would expose new spacecraft to a very high probability of collision before they reached operational orbit. Crewed missions to the International Space Station or to any future crewed facility in low Earth orbit would face unacceptable collision risk. The ISS itself, if the cascade were severe enough, would need to be deorbited to prevent it from becoming a fragment generator. Recovery from a significant Kessler cascade would require active debris removal, capturing and deorbiting existing debris objects at a scale that current technology does not exist to accomplish. Several companies and space agencies have been developing active debris removal technologies, harpoons, nets, laser ablation, robotic capture, but none has yet demonstrated operational capability at meaningful scale. The economics of debris removal are challenging. The objects removed have no commercial value, so the removal must be funded as a public good rather than a commercial service. The Outer Space Treaty of 1967, which governs state activities in space, does not contain provisions that effectively regulate debris creation. States are responsible for the space objects they launch, but there is no binding international framework that establishes debris mitigation requirements, regulates megaconstellation deployment densities, or prohibits destructive anti-satellite tests at altitudes where long-lived debris is created. The United Nations Committee on the Peaceful Uses of Outer Space has developed voluntary guidelines for debris mitigation, including the 25-year deorbit rule, which recommends that satellites in low Earth orbit be designed to re-enter the atmosphere within 25 years of end of mission. Compliance with voluntary guidelines is predictably inconsistent. The geopolitical dynamics surrounding orbital debris are complicated by the fact that several of the states most capable of addressing the problem, the United States, China, Russia, are also the states whose activities have most substantially contributed to it. The Chinese anti-satellite test of 2007 alone added a debris contribution that will affect the orbital environment for generations. Addressing this history through international regulatory frameworks requires a degree of cooperation between major space powers that has not been characteristic of the current geopolitical moment. Donald Kessler described a cascade that, once initiated, is self-sustaining regardless of what humans do. The environment generates its own future collisions from the debris of past ones. Human activity does not accelerate it further. Human cessation does not stop it. The orbital altitude bands above Earth are, in the scale of human infrastructure, extraordinarily thin and extraordinarily valuable. The 7 to 8 kilometer per second velocity of objects in low Earth orbit is the reason those orbits are useful. It provides the centripetal balance that keeps satellites aloft without fuel, and it is the same reason debris in those orbits is so destructive. We have been adding to the debris population in these shells of altitude since Sputnik in 1957. The question of whether the current population is already past the threshold, whether the cascade Kessler described has effectively already begun, slowly, and whether the collisions it will eventually produce are already determined by the physics of the existing debris field, is not settled science. The answer depends on exact densities, exact mass distributions, and exact orbital parameters that are incompletely known for the untracked fraction of the debris population. It is possible that remediation efforts and responsible behavior by current operators can maintain the environment below the cascade threshold. It is also possible that the threshold has already been passed in certain altitude bands and that the cascade is already in slow motion underway. The difference between these possibilities is not visible from the ground,